Welcome to Module 5. Today is all about the tools of the trade. In an audit, what you don't measure, you can manage. We're moving beyond the utility bills to physical data collection. We'll cover sensors, data loggers, and specialized equipment for environmental, electrical, and combustion analysis. This lesson bridges theory and field practice. Instruments are used to help converting assumptions into evidence. Poor measurements leads to poor recommendations, regardless how good the calculation looks. So everything before this module explains why, how much energy is used. Everything after assumes we can measure it correctly. Instrumentation supports building envelope, electrical and mechanical, and water audits. We'll start with basic measurement principles, then examine environmental measurement, including lighting, air quality, and thermal comfort. We then take a bird's eye view of system level diagnostics for building envelope, HVAC systems, electrical systems. Note that system level electrical measurements such as power factor and harmonics are mainly relevant for industrial or large commercial settings with larger motors and nonlinear loads affecting energy efficiency and power quality. In typical residential audits, these measurements are usually less critical. From the system level, we will return to specific equipment, lighting, ballast, motors, combustion devices to explore how we measure their efficiency. A sensor converts physical quantities, for example, temperature, pressure, or light intensity into measurable signal. Sensors are the physical interface between the building and our data. Here you see a liquid in glass thermometer, and it's an old but reliable analog tool. And thermocouple or RTD, the resistant temperature detector probe. Liquid in gas thermometer rely on expansion, while thermocouple and RTD converts temperature into voltage or resistance depending on which type. Same variable, different physics, right? All measures temperature, but each use a different physical effect to produce a reliable and readable signal. The distinctions between a sensor and a transducer. A sensor detects a change, while a transducer converts that measurement into a different form, such as an electrical signal. Here, liquid in glass thermometer and the thermocouple are sensor-only device, right? The thermocouple produce a tiny mini volt signal that require signal conditioning, maybe amplifications or transmitters to become to make the signal readable. In short, sensors sense changes and transducers converts them into readable signals. One thing about thermal mass or response time, for example, a heavy probe takes longer to respond than a thin wire thermocouple because of a reason like thermal mass. If an auditor moved too quickly between rooms, knowing a tool's response time is essential, right, to avoid recording inaccurate data. So if this auditor moves too quickly, then the measurement may not be accurate. So type of sensor used depends on the applications. A device can combine a sensor, signal processing, and display or memory data storage. They are the bridge from raw signal to data. The device on the right, it's a digital thermometer, could be a hygrometer. It shows temperature and humidity. Okay. The device with the red and green light, that's a typical state event data logger. Those lights usually indicate login or on, right? The green light, or the red light can mean alarm, low battery, stuff like that. These are used to track when a piece of equipment is on or off, on or off. Okay. Aliasing. It's if you set a logger to record, say, every 15 minutes, but a pump cycles on and off every 5 minutes, you might miss the cycle entirely. So this is why sampling rate, how often we sample, it's the most important setting on this kind of device. Okay. Before we talk about tools, we need to talk about can we trust the measurement. Every measurement has uncertainty. Accuracy tells us how close we are to the true value. Precision, on the other hand, tells us how repeatable the measurement can be or is. Calibrations ensure the device output corresponds to known standards. Right? Sensors can drift, and calibration can drift over time due to aging, temperature, handling, different kind of factors. Whether a measurement is manual or electronics, it is meaningless unless we understand its uncertainty. In energy auditing, we are rarely looking for laboratory accuracy. We're looking for decision level accuracy. Okay, so what that means is, as long as the measurement can help us making the right decisions, that's the accuracy we need. It doesn't have to be 100% perfect, right? The ruler on this slide here, it's a metaphor for precision versus accuracy. For the auditor, even the most, say, the most expensive infrared camera, right, is useless to the auditor if it hasn't been calibrated. As an example, say, let's say, how do we calibrate temperature? A temperature probe, right? We can put that, say, use a thermos and put ice and water, and the temperature has to be what? 0 degree. So if your probe read 2 degree, then what do we need to do? We need to take that into as a factor to correct that 2 degree difference, right? Finally, not all measurement requires sensors and data loggers. Sometimes maybe just manual measurement, right? Like insulation thickness, duct dimensions, damper positions are often faster, cheaper, and sufficiently accurate for audit purpose if they are measured manually. Okay. The key question is not is it digital, but if it's accurate enough to support, right? To support our audit or what we are making. Spot measurement capture single moments. right? To take a picture for a moment. While logged measurement is like a video, capture behavior over time. Building rarely operate on a steady basis, which is why logging is often more valuable than instant readings. Log measurement allow long-term tracking and help us understand occupant behavior. Okay, for example, auditors sometimes maybe they place loggers on a Tuesday and retrieve them on Thursday, missing weekend activities, right? And a building schedule sometimes is actually it's often its biggest source of energy waste. So always log at least a full 7-day week to verify that we can set back is working properly. Do not assume. Do not assume. In general, energy audit or similar studies, data logging and occupant use are two critical elements for gathering and analyzing meaningful data. So next, we will examine how data logging capture building performance over time and how occupant behavior influence energy use. Okay. So data logging measures and record building variables continuously over time, right? And unlike spot measurement that only capture a single moment at a single place. And common variable we track: temperature, humidity, relative humidity, indoor air quality, light intensity, and for operations we track hour of operations, motor equipment runtime, how long do they operate, power consumptions, different kind of event, on off cycles, and why do we use data loggers, right? It can monitor, record 24/7, provide a complete picture of building performance, more accurate than occasional spot check. It's a self-contained unit. Some can be battery powered with memory for data storage, and sometimes smart sensing as well. Usually include a sensor plus a microprocessor to record timestamps and other data as well associated with each timestamps. Okay. Yeah. So data logging help us see patterns over time, right? Patterns over time, capture occupant behavior, identify inefficiencies that spot check can miss, right? Okay. This slide shows a motor on and off logger. It uses a magnetic field to detect if a motor is running, and it can record temperature, runtime, power, events continuously. And they are battery powered, inexpensive, can be critical for identifying schedule, cycles, and operational inefficiencies. Here shows an infrared people counter, right? People they don't consume energy, but they drive load. Occupancy can be measured by people counter, or can also be inferred indirectly from equipment runtime and sensor activations. You probably have been walking into a classroom and the lights just turn on. Right? And why do we count people? Why? Well, use the people counter data, we can justify what's called demand controlled ventilation, for example, DCV. More people, more ventilation. Less ventilation. If the sensor show the gym is empty 80% of the time, you can recommend slowing down the fan to save thousands in heating, cooling costs. Okay, maybe we can do an analysis in ventilation. Okay, an activity using the ASHRAE standard procedures. Okay, remind me about that. These are the important environmental factors, measurements that can be made during energy audit or assessment to evaluate how well a building or space is performing in terms of comfort, the indoor air quality, and lighting. And we have the indoor air quality. It's some mostly related to ventilation. That's an activity we can do. Lighting level is another one. We kind of done the building envelope, right? For heat transfer through a building envelope. That exercise in our previous class. So maybe we can do the other two this time. Okay. Anyway, so these are the factors that determine how occupant experience the space. How do we have thermal comfort, air quality, and lighting? Lighting is very interesting topic actually. It's a very important architect, or actually even engineers, we should care about lighting as well. And we want to do all this while balancing energy efficiency. Okay. Here shows a psychrometer. Remember the psychrometric chart, right? It measures relative humidity based on the relation between dry bulb and wet bulb temperature. The most modern handheld device that features psychrometer functions also include sensors for carbon monoxide and carbon dioxide. Temperature alone does not define comfort. Humidity, ventilation matters too. The psychrometer and CO2 sensors help determine if the space are, say, under or over conditioned. Okay. Under, then we sacrifice thermal comfort, indoor air quality. Over conditioned, we waste unnecessary energy use, right? So this is a light meter there. And lighting audit are based on measured illuminance at the task plant. So when we do our activity, right, that plant is your reference, not the walls or the floors. It's this working plant. For example, if you're studying on a desk, then we measure the illuminance on the plane of that desk, not anywhere else. Okay. Overlighting, it wastes energy, sometimes even hurts the eye if it's too bright. Underlighting can affect productivity or even safety sometimes. System level measurement. The system level audit measurement evaluate entire building systems rather than individual components or equipment. This reveal interactive effect between the systems sometimes, and systematic very difficult to pronounce, system inefficiency. Okay. All objects emit infrared radiation, right? We are emitting thermal energies. With our body temperature, our peak wavelength will be in the probably mid-infrared range, right? And thermal imaging converts temperature difference into visual patterns, highlighting insulation gap, thermal bridges, infiltrations, okay, so on and so forth. The the object, as all objects emit infrared radiation, proportional again with their temperature, right? Infrared thermal imaging system produce a video signal that can be displayed or recorded the as a thermogram. It's a photograph of infrared picture view that shows variations in temperatures. The lighter, brighter color, it's a higher temperature. The darker ones, right? They are the lower temperature ones. Notice this is a scale here. This is a -5 to -20. I'm not sure if you can read especially the pink one here. This is -5 to -20. Here is 15 degrees C and about 6-7 degrees down here. So the scales are relative. It's not right, are relative. And so thermograms, they are qualitative, not precise R value, the R value measurements. No, they are used to identify problems, location areas, not to calculate heat loss directly. Okay, not directly. Be careful when we use this kind of tool. When using this kind of tool, remember shiny metals like the silver, maybe the steam pipe, they reflect heat like a mirror, right? So this tool will give a false low reading unless we put a piece of black tape on top. So that can we have to be careful with the technical term is called emissivity, right? The emissivity. Okay, so we want to make sure we are measuring the right temperature. Okay. So when you see something very shiny and very reflective, make sure you put a black tape before you measure the surface temperature. Air leakage, right? We know we cannot see air, we can feel air. If there's wind, we can feel air, but we don't see air. So air leakage is invisible unless you make it visible. So we can use the smoke. The smoke test shows direction, magnitude, and location of infiltrations. This is kind of essential for envelope diagnostics, right? The hand you see now is applying powder smoke and it's testing for air infiltration. Sometimes when the this kind of smoke powder, they are good. Sometimes auditor they can also use scented oil like for smell, peppermint smell on one side of the door and smell it on the other to find hidden leaks maybe in the ductwork, right? You can smell it, put it at some location, go to another location and see if there's any air movement, air path within the building. Okay. For system level measurement, one thing we can do is to set up the pressure differentials for indoor-outdoor environment. That's we are asking how leaky is the whole building as a system, right? So to answer that, we need a driving force. In buildings, air does not move reliably without a driving force, which depends on pressure difference. So yeah, sometimes they are natural drivers, wind, stack effect, but they are uncontrolled and can be variable, right? They varied. So what's called a blower door test, we blow air out of the from indoor to outdoor, creates kind of a suction, and therefore there's a pressure difference between indoor and outdoor, right? That's the driving force. Okay, so that's a non-repeatable pressure difference that we can create to do that kind of test. Okay, so I still remember when the house an auditor came to our house and doing this door test, and I was asking, how do you read that, right? And so guess what? If the house is well tightly sealed, you will create a larger, right? The delta P will be larger. If the house is very leaky, then it's easy to kind of blow the air and you have less delta P, less pressure difference. So from the readings, you know how leaky the house is, okay, or how tightly sealed sometimes. Okay, next.